go from current slide, and let me make a few announcements. This last one is the one that stings usually, so it's not that y'all are so ugly you're making me cry, it's just that the drops are hurting. Though the form, well, never mind, I won't go there. Okay. Let's go over just a couple of things before we get started. As you just realized, I've had my eye surgery on Thursday, and I was able to do almost nothing all weekend. Physically, I couldn't. I can't lift 10 pounds and I can't stoop over, okay, and that kind of stuff. So I've been pretty much immobile. And Thursday, I was sleeping off anesthesia just about all day long. I mean, I was just totally worthless that day. And then Friday, by left, I was still dilated all day long, pretty much, until late in the evening. It finally went down. So there wasn't much I could do vision-wise on Friday either. And had to wear sunglasses, deep shade inside, you know. But then Saturday, I had more of a normal day. We went to the CVS and got reading glasses because he put this lens that he did 9 years ago plus is a distance lens, so no problem there. But my regular one was close vision, and it adjusted somewhat. It's just that it was getting blurry with the cataract. So when they put a new lens in, of course, there's no adjustments anymore because those are fixed. So he put a lens in that's whose focal point, or I guess is how you say it, is between reading and computer screen. So now everything's blurry. Looking at y'all is great this way, but reading the book without, we went and found just some reading glasses that seem to work. Very, very low power, but now I can read the page. But that looks blurry, so I'll be taking them off, putting them on until I get used to it. It's almost dizzying, but it'll manage. But another issue is, I'm in class almost all day today, but then on tomorrow I do have an appointment with the follow-up visit with the doctor. The good news is, on Thursdays he's right across the street at UAB West, so I had this done at Eye Foundation Hospital, and that's real close to where we live, so that was convenient. And then the appointment tomorrow. So tomorrow afternoon, between 2 and probably 3, I won't be available. If anyone was planning to come by or ask questions or call, don't bother between 2 and 3. But I'll be here from 10:45 until probably 1:45. I'll probably allow myself a little time to walk over there and get there a few minutes early. And then my appointment is 2:10. Hopefully it won't take more than an hour. But if he has to dilate my eyes and that kind of stuff, then it may take a little longer. I don't know, I can't remember when I had this one done more than 9 years ago. I don't remember what the follow-up was like. So anyway, I'll be out of pocket for about an hour, probably, at least on tomorrow, in the afternoon, 2-ish to 3-ish, okay? Trying to think if there's anything else. I can't think of anything, so any questions for me? Oh, one other thing, now that I did remember. They did ask for us to do what they call a no-show report. And what that means is any students who had paid for the course but never has attended. Well, everybody here had paid and attended. There was no one who paid and hasn't attended, so that was pretty easy. But there were a few people who had been absent a lot. No one here, because y'all have been here almost every day, if not every day. But there were a few that have. I've heard from a couple, but they were here at least one day, so I didn't do a no-show on them. But they're trying to do it remotely, watching the videos. So now, that was people who have paid but not shown up. It hasn't got anything directly, though it would seem like it would, to do with people who have not paid and are showing up. But at some point, that's going to be the issue, and they're going to remove unpaid students from the roll. So I don't think that pertains to any of you, but if it does, even people listening at home, please get your payment worked out, or let the business office know what your plans are to work it out, because they need, otherwise you might be removed from the class, and then you have to go through lots of hoops to get back into class. But usually they'll let you, but if they get the money, okay? But anyway, that may be coming, but it has nothing to do with the one I did. But just since that happened, I thought the other might not be too far away. All right, any questions? Anything we've done so far? All right, my memory was, or Mark, anyway, my memory would be miserable, but we're on page 518. This is Chapter 8, Integration Techniques and Improper Integrals. We're going to focus on integration techniques. And 8.1 are the basic integration rules, and that's what we were going through last time. So any questions? They showed the first example and not a 1 cent. Okay, so we're on example 5, middle of page 518, and we're doing this on the screen that says 1C because they didn't do any other examples other than that first one. So here's one. Find this integral. The integral of cotangent x I'll do it the same way they did. Excuse me, log of sine x, okay, dx. All right. Leave it, let's just say, a little bit of an strange looking problem here. Keep seeing the guy here, and I think someone's standing there over me. Okay, what in the world can we do with a problem like this? Now, a little bit later, we're going to have integration by parts, and that would be the first effort would be doing that. We haven't gotten there yet, okay? So what in the world can we do with a problem like this? What's the first thing that comes to mind?
Separate it.
Separate it? Okay, like this and that. Okay? And I hope you don't mean separate by integrals, because I don't think we have a rule that says we can do that. I don't believe.
Substitution?
Second?
Substitution?
Okay. What would you substitute?
Sin x?
Okay. Okay, that has potential. But what must we also do, something else, before that will make a lot of sense? Hint, these are trig functions. What's one of the steps usually associated with trig functions? At least one of you in here was in my trig class, so you better know, Jake. Okay?
You have to substitute, I guess you can do cotangent.
Okay. Are you saying something about cotangent?
Yeah.
What is that?
Cosine and sine.
Ah, okay, that sounds helpful. Okay, so let's rewrite cotangent as the integral of cosine x over sine x times the log of sine x dx. And now, I have a good memory, it's just real short. Marjorie's suggestion sounds even better, doesn't it? Because you got a sine x in two places here. And what's more than that, you have the derivative of sine x in the other place, don't you? So let's do that substitution. Let u equal sine x. What's the next line usually? Then du is equal to cosine x dx. Ding, 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 look at there. There's a cosine x dx right there. So let's rewrite that integral in terms of u's. Okay? It would be the integral of du, that's the cosine x dx, over u times the log of u. Okay? All right. At least it looks better, looks simpler, but what in the world do we do with that? Marjorie, you want to try it again? What'd you say? Another, except we won't do a U substitution. We've already done U substitution, so this will be a, you pick another letter. Not X and not U.
Y.
Why not? Okay. So let Y equal, what would you say now? Second? I think that sounds like a capital idea. Log U. Okay, then what's the next line? dy is y is equal to 1 over u du. Oh my goodness, there we have a 1 over u du right there, don't we? So what do we got now? The integral of y dy. I think maybe even I could handle that one. What do you think that would be? Antiderivative of y dy. Oh, come on, don't tell me we went this far. Got stumped here. Y squared over 2. One more little thing. Plus c, got it. But now we got to backtrack and start filling in going backwards. What is your y? Okay, so this would be the same as log u squared over 2 plus c. But what is your u? Sine x. So this would be sine x. Wait. Oops. Sort of messed that up, didn't I? What would this be then? U is sine x, so this would be log of sine x squared, the log squared, over 2 plus c. Let's see how the, 1/2 the log of sine x squared plus c. Got it. Looked pretty nasty, didn't it? And it was nasty enough. But just about always, especially if you have multiple trig functions within something, try to simplify it. And one easy way usually is get everything in terms of sines and cosines and see if anything will pan out. Now, if you had a bunch of squares of trig functions, then you might try Pythagorean identities there. But if you have them to the first power, get them in terms of sines and cosines. And try something, and your choice of innermost part, so the most complicated looking part, yeah, that was your sine. And especially when we did that, it not only was there, but also in your denominator. That looked like a really good idea. Do that, and you wind up with yet another that we'll have to do another substitution. And sure enough, that's quite doable. But remember to backspace, backtrack. Now, if this were a definite integral, then more than likely what we do on the first substitution, change those limits, but then the second substitution, change those limits, and then try to plug in your limits so you don't have to backtrack, okay? But when you indefinite integration, you've got to always take it back to your original variable. Make sense? Any questions? All right. Well done. Medium rare anyway. Okay. So let's do, get rid of any questions for our race? Okay, too late? Okay. Let's do example 6. Find the antiderivative, or the integral or antiderivative of tangent squared 2x dx. All right. What do we do with something like this? Any ideas? Okay, certainly would be a possibility, but remember, maybe if they're squared, that might not necessarily be, it may be. We'll come back and see that. The other issue we have, we got a 2x in here too. I don't know if that's going to be a pain. Usually is, but no guarantee of it. But the more I think about it, I think your ideas, again, may be worth a shot. So what would that be? Sine squared 2x over cosine squared 2x dx. Now what?
Sub something in for cosine squared.
Second?
Sub something in for cosine squared to it.
Okay. Now the only problem with that, maybe not the only one, but a problem with it, if you substitute for cosine, the derivative of cosine is sine, and all we've got is or a negative sign. All we've got is we've got a sine squared here, not a sine. So that, I think, may cause us considerable heartburn or pain or something. So that might not be, it looks promising. If that was tangent, that's the way to go. Tangent squared, though, oh, problematic. So let's try something else maybe. Now, what did I say when you do have squares? What might you consider? Not your reciprocal identities, which is the sine and cosine, and the quotient identities or ratio identities. When you have the squares, what identities come to mind? The only trouble is it looks like a lot of mine, nothing's coming. Okay, I'm just kidding. What kind of identity?
Trig.
Second?
Trig identity?
Yeah, a trig identity, yes, it's a trig, but what kind of trig identities?
I don't know. When I see cosine squared x, I usually think that's like also like 1 plus sine squared x and stuff like that.
Yeah, what is that? What are those called? Sine squared x plus cosine squared x equal 1. One of a whole group of them called, okay. Let's go back to this. Little old right triangle here, right? This is your x, there's your y. This is hypotenuse. Okay, let's make it even better and call it opposite and adjacent. Does that ring any bells? Opposite side, adjacent side. Okay, now let's do what relates those three entities together. Right triangle, hint, hint. Pythagorean theorem, the Pythagorean identities. And what are they? What, just with what I got there? Opposite squared plus adjacent squared is equal to hypotenuse squared. Okay? Let's divide everything by hypotenuse squared. Why not? What does this give us? What is opposite over hypotenuse? sine squared, y'all know this. We'll call it theta for lack of anything else. Plus adjacent over hypotenuse, cosine squared, and you know this, is equal to 1. We don't have any sines or cosines in here, but we do have a tangent. How does that relate to sines and cosines?
Sine over cosine.
Okay, say again. Sine over cosine. So let's divide everything by cosine squared. Divide this by cosine squared. And divide that by cosine squared. Okay, what's sine squared over cosine squared? Tangent squared. Ding, ding, ding. That's what we got here. And we'll call it 2x now rather than thetas. And what's cosine squared over cosine squared? 1. Oh, I could do that one. And that's equal, what's 1 over cosine squared? Secant squared theta. Oops, 2x. Okay, I changed that. Okay, well, let's isolate the tangent squared 2x, and that would be tangent squared 2x is equal to secant squared 2x minus 1. That's another of your Pythagorean identities. So let's change this to secant squared 2x dx minus the integral of dx, 1 dx. Okay? Now, anyone want to tackle secant squared? Are we just running in circles here?
You could sub in u for 2x.
Okay. Okay, we certainly can do that, and that's a legal move. Okay. Let u equal 2x. I knew she wanted a substitution in here somewhere. Then du is equal to 2 dx, right? We don't want 2 dx, we want just dx, so let's divide both sides by 2. Okay, and then this will be a 1/2 the integral of secant squared u du, right? And we're going to leave this in terms of x's, okay? That all right with you? Okay, does that ring a bell? What? Oh, it rings bells, but you don't know. I know about that. What goes off there? It's what?
You can get tangent.
That is exactly that's the derivative of tangent x, right? The secant squared x, or u. Okay? So, this is just 1/2 tangent u. How about the next one? X. Okay, very good. But u is what? Or you are what? I'm sorry, and you need a plus c out here somewhere. Okay, so you get 1/2 tangent of, and what was u? 2x minus x plus c. All right, I hope that's what it's got. 1/2 tangent 2x minus x plus c. Ding, ding, it works. Any questions? Make sense? Okay. Remembering that, ooh, where'd that come from? Okay. Tangent squared is not the derivative of anything, but secant squared is. That's the derivative of tangent. So, yeah, you can go that way. And it's pretty straightforward. That's an ugly x there, but I guess it is an x. Okay. See if I can clean that up a little bit too much. Okay. All right. Good deal. Any questions on that? Okay. Let's scroll on through 1C. Now, fitting integrands to basic integration rules. Expanding numerators In other words, you're squaring or doing whatever you need to do. We know how to square any binomial, even with transcendental functions in them. The first squared plus twice the product of the two plus the second squared, and e to the x squared is equal to 2x. That's just one. Here's one that works on occasion. If you have a binomial or trinomial or anything else over a fixed denominator, split that up. 1 over that denominator plus x over that denominator. That's called separating the numerator. Okay? Completing the square, that's within this thing. This is a little bit of a, I don't like it in this form, but it's okay. I would put a 0 in front. 0 plus 2x minus x squared. Okay. Separate the x terms here and complete the square here. You take half of this, and you remember how to do that. But anything you add or subtract, you have to subtract or add, and then since this, that winds up being, now you get a form of 1 over the square root of 1 plus u squared, or 1 minus u squared, and that's a, go to the table, you'll see it's a trig substitution. Okay? Divide improper rational function. Anytime you have a rational function, if your numerator is a lower degree than the denominator, try something else, okay? If the numerator is equal to or greater than the degree of the denominator, divide first and then try something else. And you see this form is just going to be just like that, so whatever worked there will work here with the minus in front, that kind of stuff. Now, this is sort of a different one. Adding or subtracting terms in the numerator. We didn't see an example like this, but here's the deal, folks. Looking at this, we're going to find out later there's another way you can work this problem, but we don't have that tool in our tool belt yet. So for now, someone in the room may want to do a u substitution, okay? And if so, the derivative of this is 2x plus 2. Well, here's the 2x part, but we don't have a plus 2 in it. So why don't we just add a plus 2? But if you add a plus 2, you also have to subtract a plus 2. Well, now you have one that you can use the u substitution very nicely, minus something that has, and this is why I don't know why they didn't do this to begin with. Well, I do know. This happens to be a perfect square, and then this is just a power form that you can do. Okay? Now, we'll find out later there's another way we could have approached that problem, and we probably will. Using trig identities, cotangent squared is cosecant squared minus 1. That's just the one paired with the one we just used. It's tangent squared with secant squared minus 1. So very similar there. Multiply and divide by the Pythagorean conjugate, or just any old conjugate might work, but this one would be multiplying and dividing by 1 minus sine x. But if you do the denominator by that, you have to do this. What does that do for you? This becomes cosine squared, and then you can split this into 1 over cosine squared, which is secant squared, and this will be sine over cosine squared, which would be tangent secant, okay, if you wanted to carry that further. But yeah, do whatever's legal. You can't make up new rules, but use rules. Try several. See if you can get something that may work. Okay? And like my calculus professor said when I was, I think I told you this one, try some tricks. And if the trick works more than once, call it a method. And then go from there. And see what you can do. I do believe that may be the last slide it is of the section. Okay, homework exercises here. I know I've assigned most of these before, but do number 3 is at calcchat.com. Do any of the odds 5 through 13, they're all at Calc Chat, 7's at Calc View. Do any of the odds 15 through 45, there's a whole passel and a half of them there, so they're all at Calc Chat, 17's at Calc View. Do 47, it's a Calc Chat. 49's a Calc Chat. Either any of the odds 51 to 55, they're all at Calc Chat. Any of the odds 57 to 71, they're all at Calc Chat. 59's a Calc View. Do either 73 or 75, they're both at Calc Chat. 77 or 79, they're both at Calc Chat. You can explore doing or think about doing number 81 if you'd like. It should be at Calc Chat also. 83 and or 85, they should both be at Calc Chat. 87 should be at Calc Chat. 89 should be at Calc Chat. And then any of the odds 91 through 95, they should all be at Calc Chat. 97 should be at Calc Chat. 99 should be at Calc Chat, and then you can look at either 101 or 103. All right. Any questions? 8.1. Okay. Then let's move on to 8.2. Mentioned before, promised before, now we'll deliver, I guess, if this ever opens. And by the way, I had a message this morning that Thursday the projector was projecting blood red, and I came in this morning and it's worked fine ever since. Knock on wood. Shouldn't jinx myself here. So evidently I had problems Thursday. Maybe it was missing me. I don't know. But there's another class that uses this room on Tuesday and Thursday, and evidently it gave her problems. But fortunately today it's hanging in there very nicely. All right. Chapter 8 is still integration techniques and improper integrals, but we'll focus on integration techniques. 8.2 is integration by parts. Now, several of the ones we've just been doing, I think I may have mentioned, we'll get to another technique that'll work. I may have even called it by name, integration by parts. Now we're going to find out what I was talking about. Objective only one, find an antiderivative using integration by parts. And what the justification or the rationalization of this is, in this section you use an important integration technique called integration by parts. This technique can be applied to a wide variety of functions. It's particularly useful for integrands involving products of algebraic and transcendental functions. Okay? Now, algebraic functions are the polynomial functions, power functions, all of those. And of course, the transcendental functions are your e's, your logs, and those kinds of things. For instance, integration by parts works well with integrals such as x log x. Number one, it's a product. Okay? Now, if that was 1 over x log x, substitution, without a doubt. But this is not 1 over x log x. So, got to have something else. Here's another polynomial times the transcendental, x squared, e to the x. No single technique is going to work on that. E to the x sine x, I don't know anything that we just talked about that would do anything like that. Okay? Here's the key. You've got a product, already mentioned. Okay? Now, here's the thing you want to happen. We're going to split this into two pieces. One piece we're going to take a derivative of, that's hanging participle, I think, and the other one we're going to integrate. So we want something, usually when you take a derivative, it becomes a little easier, right? Simpler. And when you integrate, it usually gets a little more complicated, sometimes. But if you can do something that the derivative gets easier, which you want it to do, but the integration doesn't get much worse, then that's when you use integration by parts. Okay? For instance, this one, when you take a derivative, that gets simpler. Well, let's see. We'll get to this later. This one, derivative of this becomes simpler when you take the integrate this, it doesn't get any worse. It stays e to the x. This one, you could do either way. Take a derivative of that, it doesn't get any worse. Integrate that, it doesn't get any worse. So these are prime examples. This one is a little stranger. We'll get to that a little bit later. So here is the justification or rationalization for this, our good old product rule for a derivative. Okay? We know that derivative of a product, u times v, you tell me, what is that? Derivative of u times v. Oh, you're through at Cal 1. We don't need that anymore, do we?
The product rule, right?
Is what?
The product rule.
Yes? Fill me in. Pretty simple. uv prime plus vu prime. That's it. Product rule. Ring bells? Good. Okay? Now, this is true when both u and v are differentiable functions. Well, if we had a product rule that worked like this, it'd be pretty easy to do. But here's what we're going to do to this. Okay? We're going to take this, and what if this, maybe I should stay in red, but I think I'll go to dark. What if this is what we had? A product of two functions. One was a derivative of another. The other wasn't too hard to integrate. Okay? Let's do this. uv prime is equal to uv prime minus v, let's call it du. I'm going to go back and call it d's. Because that's going to come in a lot handier later. Okay? u dv is equal to d of uv minus v du. Okay? If this is what you got in the thing and you don't know how to proceed with it, there's no way to obviously integrate that. This is easy to integrate. You integrate a perfect derivative and you just get the uv. Right? Fundamental theorem of calculus, part 1, I believe it is. Okay? Minus this. Well, see, how did you get this? You integrated this, took a derivative of that. And if this got simpler than this was really simple, then you may have a hope. Okay? So if this is what you're trying, let's try this. You'll split and say let u be one and dv another, derivative of this, integrate that, and then this is a piece of cake, you just write it down, and we'll go. That's the basis for integration by parts. Okay? I'm not sure why they call it by parts. By parts of the product rule, I don't know. That's as good as any. So when u prime and v prime are continuous, that's good to know, you can integrate both sides of the equation to obtain this. Okay? Oh yeah. Of this thing. Right here. Integrate this, you get uv, integrate this, and integrate that. You get, this is what I was saying. This you get this. This you get uv prime dx. This you get v u prime dx. That's the integrating this. And you can rewrite this as this is dv dx, and just make this u dv plus the integral of v du. Okay? Then, that's where you do the subtraction. And if this is what you're given, then this minus this. If you've done this in a certain way, that this got easier and this got no worse, then you've made progress. So this is what our procedure is. If u and v are both functions of x, have continuous derivatives, then the integral of u dv is the same as uv minus the integral of v du. That's the basis for integration by parts. Okay? The formula expresses the original integral in terms of another integral. Okay? Depending on the choices of u and dv, it may be easier to find that second integral than it did the first one. That's our goal. Find a combination that makes it easier to integrate. Because the choices of u and dv are critical in the integration by parts, the guidelines below are provided. Okay. Try letting dv be the most complicated portion of the integrand that fits the basic integration rule. Then u will be the remaining factor of the integrand. Okay? I'm okay with that up to a point. Try letting u be the portion of the integrand. Okay, this is where I come in. The portion of the integrand whose derivative is a function simpler than u. That's what I was getting at. Then dv will be the remaining factor, and hopefully when you integrate that, it won't get any worse. dv always includes the dx in the original integrand. So the way I'm going to say that, make sure the d on both sides anytime there's a d. Okay. When using integration by parts, note that you can first choose dv or first choose u. It doesn't matter. Okay? After you choose, however, the choice of the other factor is determined. You can't go back. Oh, no. It must be the remaining portion integrand. Note also that the dv must contain the differential dx in the original integral. They already said that on the last slide. They're saying it again. It must be important. Okay? So here we go. Find the integral of x e to the x. Any audit think you can just do that right off the top? Substitution, any technique you might want to use? I think not. Huh?
U substitution?
You want to try it? What would be your u?
I don't know.
Yeah, not going to work. Okay? A simple u substitution will not hack it on this. But that is a product, so integration by parts should come to mind. And here you get to choose. Let u be something and dv be whatever else is there. Okay? Now, the dv part always has to have the dx in it. The d's go together. Okay? So what we do is pick which part is which. All right? And again, my rule, the book's rule too, is let your u part be the thing when you take a derivative, it's going to get simpler, and the v part is when you integrate it, it's not going to get any worse. So which part might you think is what? Say again? X be u? Yes, I agree. Let u equal x, and then dv equal e to the x dx. Everything else, including the dx, d must go with the d. Okay, so what do you do with the first one? It looked like a u substitution, it sort of is. Then du is equal to, second, 1 what? dx, exactly. Be sure your d's always are accompanied by another d. Now this one we're going to integrate. And v would be what? What's the antiderivative of e to the x? E to the x. Now don't include the dx there because the d's go together. Okay? And don't worry about a plus c yet. We'll do that at the end. Okay? Now, what do you do now? So this integral you first had is going to be your u times v, so multiply those two together. That's going to be your x e to the x, u times v, minus, always a minus, the integral of your bottom line, right? What do you have left? What is your v? E to the x, and what is your du? Dx. You know, that's x e to the x minus, now, I think I can probably even do that one. What would that be? Antiderivative of e to the x dx. Oh, my favorite function of all time. E to the x. That's the beauty of that. E to the x. There you have it. Now you can add your plus c. Okay? There is your that integral that we didn't know what to do with. None of our techniques would work. U substitution, nothing else would work. Change it. In some sense, it looks more complicated, but it's, split it up with your integration by parts. Do part of it as a u and part of it as a dv. Choose those that when you take the derivative of the u, it gets simpler, and when you integrate the dv, it doesn't get any worse. Okay? When you do that, then your uv is your first part. That's easy. Minus what's left over on your bottom line here, the integral of the du. Okay? And sure enough, it made the second integral much simpler. The first is already done for you, and you can just almost write down your answer. Does that make sense? All right, good deal. That was example 1, and that's what they got, but let's watch how they did it. All right, to erase? Any questions before I do? Okay. To apply integration by parts, you need to write the integral in the form of u dv, and there's several ways to do this. Why do they show you all this? But here's one way, u dv. Here's another way, u dv. Here's another way, u dv. That's ridiculous to do it this way. That's exactly what you started with. Okay? And this is that way, which is pretty crazy itself. That's when you do a du, you don't have product rule here. That's gotten a lot more complicated. This one, to whatever you do, you've got exactly the same thing as that. That got you nothing. This one, you take a derivative, that gets no worse. You integrate this, it gets worse. That would be 1/2 x squared over 2. So that one's out. This is the one when you take a derivative of this, it gets simpler. Integrate that, it doesn't get any worse. In fact, it stays just about the same. That's the one to go with. Okay? The guidelines for integration rule in the earlier slide suggests that first option, because the domain u equal x is simpler than x. No, the derivative. Okay, I can't read. The derivative of u is simpler than x. Is just dx, and the dv is no more complicated. Okay, so the d. Goodness gracious, they dragged this out unbelievably. The dv is e to the x dx. The v is and okay, yeah, okay, they're doing the integral. If dv is e to the x dx, then integrate both sides, you get v is equal to integral of dv, which is the integral of e to the x dx, which is equal to e to the x. Yes, okay. They took something really simple and wrote it so many different ways that made it complicated. The u of x is equal to, u equal x, then du. That looks just like our good old favorite u substitution there. Du is equal to dx. Now the integration by part produces u times v. There's your v over there, e to the x. Your u here is x, so that's e to the x minus, or x e to the x, minus the integral of, the way I draw it is the bottom line, the way they draw it is the right-hand side, okay? V du, which is e to the x dx. So it's e to the x, or x e to the x, minus the integral of e to the x dx. And that's simply x e to the x minus e to the x plus c. To check that, differentiate this thing right here and see if you obtain what was originally in here. So you take derivative of this, and that's the product rule. X e to the x plus e to the x minus e to the x is x e to the x. Yeah, that's exactly what you got. All right. Have we beat that into the ground? Totally. Okay, good. As you gain experience in using integration by parts, your skills determining the u and the dv will increase. The next summary list indicates several common integrals that's with suggestions for the u and the dv. Now, I'm not sure that that's in the right place. I think we've got a few more to do before we get to that summary. Whoever the graphics person was really lazy. They did one example and went to the summary. Did that in the last one and doing it again here. So let's do example 2 before we go to the summary. All right. How about this one? Integral of x squared log x dx. Any of you think of any neat, simple, basic rule to do that one? Hang it up. Nah. Okay, so what might we choose to do? Okay, here's the first suggestion I heard. Let u equal x squared, and that would then produce dv equaling what's left, log x dx. Okay? Before we go much further, let's take a look at this. Can you integrate log x? I can't either. Okay. Yeah, that's the problem here. That one, I can't think of a way to integrate it. So even though it disobeys part of the other previous rule, I don't see any way around changing that and let this be my log x and this be that. Admittedly, that's going to get worse. I have to buy that, okay? So this will be log x, and dv is equal to x squared dx. Okay? That's an ugly x, isn't it? It's getting worse. Okay. Let me see if I can clean that up. Let's just start over. All right. Then what? Then what? du is equal to 1 over x. There's more to it. dx, okay. And v is equal to, ooh, this gets worse, doesn't it? What does it become? X cubed over 3. Did I hear that? Okay. Admittedly, that's worse, okay? But going the other way, we couldn't do anything with the log x. You couldn't integrate that. So, then this thing that we had to begin with is first your uv, which would be x cubed log x over 3. Well, that's messy, but that's by itself. We don't have to integrate that. Minus, now what do we have here? The integral of your bottom line here. What happens when you multiply those together? Anything? Well, I'll have a 1/3, I know that. And this x goes into one of those two, leaving us 2 left. And what do you have then? Integral of x squared dx. You know, I think I can handle that. Okay? What does this give you? Well, just write that down. X cubed log x over 3, or 1/3 if you want it that way, minus, and what would this give you? X cubed over 3 again, okay? And now you can put your plus c. Don't forget your plus c if you got indefinite integrals. So what do we have? I'm going to write it. I think I'll pull out the fractions. 1/3 of x cubed log x minus 1/9 x cubed plus c. And if you wanted to, I don't need that first parentheses, do I? Oh, it didn't take. There we go. No, I did need it, didn't I? Okay, sorry. I thought I did, okay. If you wanted to pull out a 1/3 or a 1/9, you could do that. 1/3 of x cubed log x minus 1/3 x cubed plus c. Or if you want to pull a 1/9 out, then it would have a 3 here and no fraction here or whatever. It doesn't matter. Any of those are perfectly fine expressions of your solution, I think. Let's see what they got. They got x cubed over 3 log x. I didn't quite write it that way, but pretty close. Minus x cubed over 9. I didn't quite write it that way. Plus c, yeah. All those are the same. And you can take this, differentiate, and see if you get what was originally in your integrand. You will. Probably not totally intuitively obvious right now, but you will get it. Any questions? Make sense? All right, good deal. That was example 2. All right. Sometimes it doesn't even look like it should be an integration by parts problem, such as this one. And this is going to be a definite integral here, but this isn't what makes it unique. It goes 0 to 1 of, I don't like arc. I don't know why, it's just more to write. I want to put, well, maybe in this case I'll write it. Arc sine, ARCSIN, of x dx. Now wait a minute. I don't know a function that you can take a derivative of it and get arc sine. I just don't know one. Okay? I can take a derivative of arc sine, maybe, and get something. I can look that up in a table, but I don't know of any function that if I take the derivative of it, I wind up with an. So I can't take an antiderivative of arc sine. Okay? But let's see, I can take the antiderivative of dx. Okay, I can do that. Okay? So in this case, strangely enough, let's let your u be the arc sine of x, and dv, that's ugly, let me take it back. Be simply dx, okay? Can't get much easier than that one, okay? Then, what's du? As I said, I basically go to a table. Why? I think I do remember it, but I don't want to trust my memory, okay? And if you are working for me, I don't want you to trust your memory. I want you to know for certain what that is. And let's see, inverse sine. Is that on this page? No, it's not. Okay, here we have. If you go to the front of your book or find it in whatever book you have, front of this book, Derivatives and Integrals, number 19 under Derivatives, the derivative of arc sine is 1 over square root of 1 minus u squared, x squared. 1 over the square root of 1 minus x squared. Okay? The d's go together, so you got to have a dx with that one. Okay, that was a hard one. The easy one is what? Integrate both of those and what you get? V is equal to x. That's so good. Okay? Now, let's go back to your original, and you do your u times v, so that's those two. That's going to be x times the arc sine of x minus, here is a catch. With definite integrals, you also evaluate this part from 0 to 1. Okay? Even though you didn't do an integration to get there, you evaluate that from 0 to 1. In fact, you sort of did do an integration to get there. It's just the integral of itself. So you do that minus the integral of the bottom line here. And that would be x over the square root of 1 minus x squared dx. Okay. And this is from 0 to 1. All right. This first one, plug in the top value, and what do you get?
Arc sine of 1.
Arc sine of 1. Okay. And does anyone know what the inverse sine of 1 is? Say again? Pi over 2. Okay, so this is pi over 2. Because you always assume you're dealing with radians, remember? Always. And what's the, if you plug in a 0, what do you get?
0.
0 on both parts. So yeah, so the first part is just pi halves. Minus, this is going to make somebody's day, I bet. Okay, I don't even think I want to write that yet. How would you do this one? Say again? I thought it would. Yeah, so u substitution. What is going to be your u substitution?
1 minus x.
1 minus x squared. Then, what's the next line? du is equal to?
2x.
Minus 2x
dx.
dx. Great. Well, we got an x dx, not a minus 2x dx, so let's divide both sides of this by minus 2. Okay? Now, so minus 1/2 comes out in front, so that's going to make that a plus sign. 1/2, the integral, and these go away, so this is, I already took the minus 1/2 out front, so this is just going to be your du up here over what? Square root of u. Can I write that in, rather than square root of u, in u to the 1/2? I couldn't think of what you call that, okay? Actually, I really want to rewrite that too, but I've left off my units. I mean my limits. Okay, we got to plug those in. When x is equal to 0, what is u? Or what are you? X equals 0, what's u? 1. Okay. And let me find my pen. And find. Okay, is it Kayla?
Mm-hmm.
Okay, I thought so. All right. Good deal. Okay, now, when I plug in the 1, what does u become? 0. Now, what's somewhat problematic here? Now, this first one was just pi halves, so I'm just going to write down pi halves. What is problematic here? You got the lesser one on top and the larger one on the bottom. So what can you do with this? Flip them and what? Change the sign, negate it. So that it was a minus, it became a plus, it goes back to being a minus again. So minus 1/2, and I'm also going to write this from 0 to 1, because we flipped them, that's what changed the sign. And write this as u to the minus 1/2 du. Okay? Now I'll ask you, yes?
What made them flip the first time?
What, the sign?
Or the 0 and 1? What made them like swap?
Oh, well, okay, it was 0 to 1. Okay, when we went to a U substitution, which you came up with the idea, okay, when you do that, you see when x is equal to 0, put a 0 in here and u is equal to 1. Well, that goes down here on the bottom. Okay, and when x is equal to 1, this goes to 0 and that goes up top. So that's what made them flip. Okay, it was your fault. Okay, so, okay. And I laugh at this class in that we're segregated, the men on this side and the women on this side. You fit the mold, you continue the practice, fine with me, I don't care. Okay, this is old time calculus here. Okay, minus. Now, I'll put the 1/2 in here. What's the antiderivative of u to the minus 1/2? U to the 1/2. 2, okay, 2 times it, over 1/2, which is time, yeah, okay. And now the 2's go out, which is very nice, and this is evaluated from 0 to 1. Okay, so we got pi halves, that was left over from the first part, the uv, minus, and what do we have here? Square root of 1 is 1 minus 0 is 0, so it's pi halves minus 1. I hope. Yes, pi halves minus 1. And by the way, for any who want just a general idea of pi halves, that's, since pi is 3.14, this is about 1.07, 3.14, 1.57, okay, 1.57 minus 1, would be about 0.57, which is what they come up with, about 0.571. Good deal. All right. Now, there's a little technology blurb at the bottom of the page, and I really don't want to spend too much time with that, but underneath that, there's a thing that says, for further information to see how integration by parts is used to prove Stirling's approximation. Oh yeah, that. Okay. Here's an article they refer to that is a physical chemistry project in the Journal of Chemical Education. That would be a legitimate paper topic, you know. Or who in the world was Stirling in the first place? It's probably going to be a physical chemist or somebody, but anyway, you might see that. But you could use that paper to do an article there. So there's all kinds of possibilities there. Okay. Any questions on example 3? Okay. Let's move to example 4. And this is, you have a book or you're using your book. So whatever you can find integration by parts in there, I bet you it has a top section named it, okay? But let me erase this if I can find it again. There it goes, okay? And let's do example 4. Here we have an integral, x squared sine x dx. I think this is one we saw earlier or something pretty close to it. Any of you think of a fundamental technique that might work? Tabular form, something like that? I think not. Okay, but this is set up perfectly for integration by parts because it has a product, okay, which is nice to have. Don't always have to have it, but nice to have. One part will get simpler by integrating, differentiating it. The other part doesn't get much worse by integrating it. So how might you proceed? Let u equal x squared. That sounds like a winner. That leaves dv to be everything that's left. And what's that? Sine x dx. Remember, the d's have to go together. Next part here, then du is equal to 2x dx. Okay? And v is equal to negative cosine x. Because the derivative of cosine is minus sine, so the derivative of minus cosine would be positive sine. Yeah, that works well. Okay, so what would this produce? First do your u times v, which is minus x squared cosine x. Okay, now let me make sure they didn't put any limits. They did not. Okay. Now, that minus is because of that, okay? So that's by itself. But that's followed by a minus, and that doesn't change to a plus. There's no reason for it to. Yet, there may be, we'll see, the integral of the bottom line. And there, the minus shows up again, so this does become a plus then. And what goes in here? And I think I'll even pull my 2 out here. And what goes in the integral? Second, x cosine x dx. Okay? Now, I'm okay with that first. Nothing else we can do with it. There were no limits on the integral, so we're fine here. But what about that second integral? Play it again, Sam. Nothing you can do except do another integration by parts. Now, warning. Don't reverse them. Don't say, well, last time I let my u be x squared, that didn't give me, let's reverse them now. You reverse them now, you're going to go back to where you were. Okay, let's not do that. You know, let's keep going forward in pretty much the same order. So guess what? You mind using u and v, or do you want to change letters? Yeah, I'm okay with that too. Let u equal what now? X, and dv is equal to whatever's left, cosine x dx. Okay? Then du is equal to dx. Now it's going to get a little simpler. It did last time, but this is really simple. And what's your v going to be? Sine x. Okay, perfect. Now, for this part, we're going to let u times v, so this will be plus 2 times x sine x minus the bottom line, the integral of sine x dx. You see that? Sine x from the v part, dx from the other part. All right, don't forget the 2 is in front of all that. So this is going to be our final go through here, or close to it anyway, minus x squared cosine x plus 2x sine x. And what's the antiderivative of sine? Say again? Negative cosine. So that minus is going to make that a minus. So this will be plus 2 cosine x. And then one more little thing. Indefinite integral plus c. Don't forget your plus c. All right. Let's see, what was that example 4? would be minus x squared cosine x plus 2x sine x plus 2 cosine x plus c dot. Okay? And then they do the same little thing. When you're doing it, don't interchange your substitution in subsequent applications. Just go in circles then. This feels enough like you're going in circles, but at least you're getting simpler. If you do it the other way, it doesn't get any simpler. You wind up right where you started. All right. Now, excuse me, example 5. Any questions on 4 before we leave it? Okay. Have we been going about an hour and a half? Need a break? Do? Okay. So before we go to example 5, let's do a pause here. All right, that was example 4. Example 5. No questions? Let's pick up and go from there. Oh boy, find the antiderivative of the integral of secant cubed x dx. Uh-oh. What in the world are we going to do with that? Second?
Make it secant squared x and secant.
Oh, clever, clever. Yes, yes, let's do that. Make that the integral of, how do you want to write it? Secant squared x times secant x dx. That's legal in most states, right? All right, now what? Let u equal, I'll do that part for you, okay? That's the hard part. Now, what do we want to be our u?
Secant squared x.
Okay, and then when you do a du, it gets a little, I don't know, 2 secant x times secant x tangent x. That's not a whole lot simpler, is it? Most of these it would have been. In this case, not. So what's the other option? Let u equal secant x. Then, well, you don't have to put then. I would say and, or just put a comma or a semicolon or something there. The next part would be dv is equal to what? Secant squared x. Now, why would we do that? And of course, it has to always have the dx. The d's go together. Okay? Then, bad news, what does this give you? Say again? du is equal to? Say again? It's secant x tangent x. Remember, that's a weird one. dx. But what is dv? Okay? It's antiderivative of secant squared. Tangent x. Oops, I should have put v equal tangent x. Because the derivative of tangent is secant squared. Okay? That was the whole reason to do the dv there. That gets simpler. Okay? A lot simpler. Okay? Actually, your u got a little more complicated, but your v got much simpler. But I still don't know if this is going to do us any good until we do the next part. So our integral here will equal u times v, which is secant x tangent x minus the bottom line. And that would be integral of secant x tangent squared x dx. Okay, I don't like the look of that at all. Okay? But, let's see. Are secants and tangents in any way related to each other? Third cousins, twice removed, or something like that?
Their cosine is on the bottom
Of both of them, so that would be 1 over cosine times sine squared over cosine squared. I don't think that's going to help us a lot. But when you see the squares, what should pop into your mind? Lights going off. Pythagorean identity. How about tangent squared and secant squared there? What would tangent squared be? Say again?
Secant squared minus 1.
Secant squared minus 1. So let's try that one. I don't know if that's going to work, but let's try it. Secant x tangent x minus the integral of secant x times, what do you say? Secant squared x minus 1 dx. Okay? Beginning to feel I'm running in a circle here. Are y'all getting the same feeling? Because what does this give us? Secant x tangent x minus integral of secant cubed x minus secant x. Well, let's just split this into 200. Secant cubed x dx minus secant x dx. Okay, now wait, we got too many minuses in a row. That second one better turn into a plus, right? Okay. Now, okay. Now, have you noticed we started here and we wound up there with some more mess involved? In fact, this doesn't even sound like this should be true because, well, yeah, I guess it could be. But let's see. What we're looking for is this anyway, so why don't we add this to both sides of the equation? Here's your equal sign, and this is on the other end, few equal signs over, integral of secant cubed x dx. Here, add it here, integral of secant cubed x dx. Okay, so this gives us two of those babies. 2 integral of secant cubed x dx. And what's that equal to? Secant x tangent x, that's from here, plus the integral. Now what is the secant x anyway? Oh, it's 1 over cosine, isn't it? Let's do cosine x to the minus 1. That's not an inverse cosine, okay? That's one advantage of art things. This is one I think is time for the table. We had this before, I don't know if you recall that, but it's one I don't like to remember, so I'm going to go to the table on this one. The integral of secant x, and in your text, you can find that if you have this text, or whatever text, you have a table somewhere, and in this one, on the front inside cover, it's log of secant u x plus tangent. x. Okay, so let's not go with inverse cosine. I thought that, not inverse, reciprocal of cosine. I thought that might work, but, well, let's just do the secant x from the table. Remember, we legitimized that before. What did I just say it was? Log of absolute value secant x plus tangent x. And then you do your plus c. Okay? You make sure that's right. Yep. Okay. Now, all we have to do is divide by 2. We can leave the plus c out. So it's 1/2 of that thing right there. And they actually split it up and say 1/2 of secant x tangent x plus 1/2 the log of secant x plus tangent x. And then, I don't know why you want to do this, you could have taken that 1/2 and put it up here and do the square root of that thing, if you wanted to, log of the square root of that. But I don't think that's any simpler. Okay. And that, sure enough, is what they got. Now, this is a case that by following through and then doing your you get to the point where you have the same thing on both sides. Now, if this had been a plus here, you're really in serious trouble, okay, because then the subtraction would be a 0. But if this is a minus, then take it and add it back over here, giving you 2 of these things, and then whatever else this works out to be, that you can then take 1/2 of that, and that's what we did. Usually a book will find a simpler one than this to show that technique, but it can happen that you wind up going through your procedure and you wind up with the same term you're trying to find the integral for, add it to both sides. Now that's not if you have reversed the order of doing things and you wind up, then you'll get 0 equals 0 or 7 equals 7. You'll get an identity that won't matter. This actually gives you an answer. Okay. All right, that was example 5. Example 6 is trying to be a little more practical of a problem. So let's see what we've got there. Any questions on this one before we leave it? Okay. Example 6. A machine part is modeled by a region bounded by the graph of y is equal to sine x and the x-axis, and as long as x is between 0 and pi halves. Okay? Now that's almost simple enough. I can draw that one. That's supposed to be a sine function. Okay? Goes up to 1 here, and this is pi halves here. Okay? And this is your part. Okay? That's a pretty ugly drawing. The one in the book's a little bit better. Okay? And you stop at pi halves here. I can't get it to draw. There we go. Okay. Find the centroid of that region. So we're assuming this is a laminar plate, you know, uniform density, all that kind of stuff. And you want the centroid of that region. Okay? Now, they say, this is from the last thing, it says, begin by finding the area of the region. Now, most of the time we said the mass of the region, but remember we're assuming the density is 1. That's what they do with centroids. So the area will give it to you. So let's just find the area. This will be the integral of from 0 to pi halves of sine x dx. Height here is sine x, width is dx, okay? And you sum those from 0 to pi halves. So there's your, what is the antiderivative of sine x. What? Say again? Negative cosine. Negative cosine x evaluated from 0 to pi halves. That's a pretty ugly pi. Okay? Not that pi's are usually ugly, they're usually pretty nice to me. Okay. Now, plugging that in, what do you get?
-1 minus.
You get what?
Well, cosine of 0 is 1, so you get -1.
Negative a negative 1, which would be 1. Okay. Yeah. Start with the pi halves part. Cosine of pi halves is 0. So that gives you nothing, right? Okay. Minus a minus cosine of 0, which is 1. Right? Minus minus. Cosine is 1. So that's 1. So there's the area of 1. Okay? Fantastic. Okay? Now, it says now you can find the coordinates of the centroid. First evaluate the y bars. Okay. Now, the y bar will be represented by that point there. Okay. And you're going to sum those centroids of the whole thing. Well, what is the distance from the y-axis your height of this thing is sine x, of course. Okay, and your distance from the y-axis is half of that. Okay, and that's what you're summing up. And then you're dividing by 1, so that's really easy. I'll take care of that. So your y bar is the mass of this one little strip, which is just sine x dx, times the distance from the x-axis. That's what y bar is, and that's half the distance, so it's 1/2 the integral from 0 to pi halves of 1/2 sine squared x dx. Okay. Now you'd also have a 1 over the area, and this is your area, but this is just 1. Okay, so you don't need to worry about that. You can divide by 1 anytime you want to. Now, how do you do this one? They go to a trig identity, which for some reason I'm guessing that many of us probably haven't remembered. Seemed like that was the case in my first class. I don't know if it's the case in this one too. What is sine squared in terms of a half-angle formula? You remember that? If not, most of your calculus books will have in somewhere a little page on trigonometric identities, and I'm sorry, it's a double. Yeah, it's what they call a power reducing formula, which also comes from your half-angle formulas. Okay, and sine squared is 1 minus cosine 2x divided by 2. Okay, and they use it in the book, so it's fine to use that. So this is going to be, it's another 1/2, so that's going to make a 1/4. I'll write it down for you here. Sine squared x is 1/2 1 minus cosine 2x. I think make sure I did put the sign correctly. Yeah, I already did the 1/2, so I don't know why I put that up so high. But that's what it is. So the 1/2 comes outside, and this will be the integral from 0 to pi halves of 1 dx minus the integral from 0 to pi halves of cosine 2x dx. Okay? Be 1/4 antiderivative of 1 dx. X evaluated from 0 to pi halves. Pi halves, okay? So that's your pi halves. That's from that one. That was pretty good. Now this one will take just a little more thought. What's the antiderivative of cosine 2x? It's this minus is already there. The antiderivative of cosine is sine. Derivative of cosine is minus sine. Antiderivative is sine. But you got the 2, so unchaining it is another 1/2 sine 2x. Right? And that's evaluated from 0 to pi halves. Okay? Now, let me close off my other parentheses there. So this will be 1/4 pi halves let's just pull out a 1/8, okay? So we don't have to worry about so many fractions here. Okay, it didn't take, there it goes. Well, I'll leave them up there, but take them out down here. Okay, 1/8, and this will just be pi here. Okay, now, pi minus. Okay, now we got the minus in front. Cosine, well, 2 times pi halves is pi. Sine of pi is
0.
Wait, yeah, you're right, absolutely. Sine of pi is 0. So this is going to give us a big fat 0, isn't it? So it looks like just a pi eighths. Could it be? Yes, it is. That's all you've got is pi eighths divided by 1, which of course is pi eighths. Okay, now that's the y bar. The x bar, okay, it's going to be that same area here, which is sine x dx, which is your volume, I mean your mass too, with the density of 1, okay, times your x. So it's going to be, where can I write this? Let me erase some up here at the top, because this was just to remind you what the half-angle formula was, or power reduction formula. Okay, so let's do our x bar up here, and that's going to be the integral from 0 to pi halves of your x sine x dx. I know you're wondering where in the world that this problem is ever going to get around to an integration by parts. We got it. Okay. That's the only way to do that one, is integration by parts. So how does that go? Make sure I've written it right. I believe I have. let u equal x, is that what you said? And du is equal, dv is equal to, okay, my writing is really ugly, is what? Sin x dx. That makes then the du equal dx, and the v equal to it's negative, isn't it? Yeah, because derivative of cosine is negative sine. Okay, so this integral will be your uv, which is minus x cosine x, evaluated from 0 to pi halves. Remember, when you have a definite integral, even that first part, you have to evaluate between those things. And then you're going to have a minus, but this is, your bottom line is going to have a minus, so that's going to be a plus the integral from 0 to pi halves. Cosine x dx. Okay. Whew. All right. So let's evaluate that integral. Okay. Evaluate this one. The pi halves. 0. This is 0, and this is 0. Yeah, it doesn't. Okay. This is negative pi halves, and this is 0, right? Okay. And then at 0, this is 0. So that whole first term is a 0. Nothing. Okay. So all of our answer is over here. And what's the antiderivative of cosine? Sine x evaluated from pi halves to 0. And that's going to be 1. All right. X bar is 1. So with pi halves being 1.57 approximately, this will be about 2/3 of the way out, and your y bar was about pi eighths, which is close to 3/8, so less than half the way up. So basically somewhere right about there is going to be your centroid. 2/3 away from the y-axis and 3/8 of the way up approximately from the x-axis. All right, finally, we're ready for our summary that they were ready for after example 1. Common integrals using integration by parts for integrals of the form x to the n, any power type form here, e to the any kind of exponential here. That's going to be fantastic for integration by parts. This will be your x, that will be your dv. Okay? Same thing here, any power for x times a sine or a cosine, they're going to be, here's your u part, there's your dv part. Because the sine and cosine just back and forth between sines and cosines, pluses and minuses and all that kind of stuff. You just do it until you get tired of, until you come up with an answer. Okay? But every time the u will decrease. You may have to do it multiple times, but you have to keep counting down the end there. So let u equal x to the n on any of these, and dv be either the e to the x, the sine a to x, or the cosine a x. Okay, now if you have this kind of form, integral of x to the n log x, okay, remember, since we can't integrate a log x, that has to be our u part. But that'll give us a 1 over x for a du, which is going to reduce this one back to where it was, so the u will be the log x, okay? Now on this part, you'll be the inverse sine, because you can't, same reason. There is nothing that you can integrate this to get anything. So, but you can take a derivative of this. This is 1 over square root of a minus x squared, or a squared minus x squared, something like that, or 1 over a. Anyway, that's all doable by taking the derivative of this. This will get messier, but it's not a great deal messier, and you can use some of those in doing this, because this has a square root of 1 minus a squared, that kind of form in it, so you need x to the numerator with the dx to simplify. Same thing here, this is going to be not square root, but 1 over a squared plus x squared, or something of that nature, and so you can use these in the numerator to balance out those. So your u's will then be the things that you can't integrate, the log, the arcsine, or the arctangent. Okay. The dv will then be this. So sort of backwards from our thinking here, but it has to be that way because you can't integrate those. And then integrals of the form of e to the x sine bx or e to the x cosine bx, it really doesn't matter which one you do. A little easier to let the u be the sine or the cosine, because we make fewer sine SIGN sine errors with those when you take derivatives. We make more errors when we do antiderivatives. But these are just easy. They don't get any worse. These don't get any worse if you put them there, but it is harder to keep track of the SIGN signs, whereas it's very easy to keep up with that there. Okay, so let these be the U's. Again, it really doesn't matter, but please don't, if you have multiple of these to do, don't do one time let this be the U and that be the dV, and then the next time let that be the dV, because you're going to go nowhere with that. Okay. So in problems with repeated application of integration by parts, a tabular method illustrated in this next example, example 7, can help organize the work, and this method works well for integrations of this form. When you have x to the n, sine ax, cosine ax, or e to the ax. Okay? Because, as you see when you do this, if you create the table, the patterns, you take advantage of the pattern nature of it. Okay? So, you can also go to larsoncalculus.com and see an interactive version of example 7 as well. So here's example 7. We'll do an easier one. We won't take n equal 45 thirds, or something like that. We'll keep it n equal 2. Okay? So, what would be your first take on this? X squared and dV equal sine of 4x dx. Don't forget, the d's go together. Okay? Now, what's your next step? du is equal to 2x dx. The d's go together. And v is equal to v is equal to v is equal to anybody help me? I'm stuck up here. First, the antiderivative of sine is negative cosine, so we're going to have a negative cosine in here of 4x, but then you have to do an anti-chain rule type thing, so that would be a 1/4, exactly. Okay. Now, your I don't know if I really want to mess with their table thing or not, but it is okay. What we have here then is your UV is minus 1/4 x squared cosine 4x, right? U times V. Now you have a minus, because you have a minus down here, so that's going to be a plus the integral. Oh, let me do. You have a 2x here and 1/4 here, so that's going to be a 1/2. 2 times 1/4 is 1/2. And you have the, x cosine 4x dx. Okay. Now, can't do that, but, okay, let u equal x, dv is equal to cosine 4x dx, then du equal dx, and v is equal to, what would that one be then? Yeah, 1/4 sine 4x. Okay? So, this will be, the 1/2 is there by itself. Okay? It's outside of all this. Your UV is 1/4 x sine 4x. And this time there is a minus, your bottom line here. And there's another 1/4, the integral of sine 4x dx. Okay. Now I'm going to pull the 1/4 out with the 1/2 and make that a 1/8. And this, oh wait. About to forget my first term here. I did forget my first term. Okay, a minus 1/4 x squared cosine 4x plus 1/8 x sine 4x minus, I already pulled the 1/4 out, what's the antiderivative of sine 4x? Negative, so that minus of minus is going to make it positive. Cosine 4x with something else. 1/4, perfect. And then at the end of all this, we'll put our plus c. Okay? So let's see what we got now. Minus 1/4 x squared cosine 4x plus 1/8 x sine 4x, and then I think we got a plus 1/32 cosine 4x plus c. I think I got them all in there. Let's see. 1/4 x squared, yeah, minus 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 1/32 cosine 4x plus c. Now, if you see the tabular method is helpful there, by all means use it. I mean, it's perfectly fine. And I guess it's helpful to do, but I just can't see that it's much simpler than just doing it. I guess if the n was a much bigger number, then after a while, yeah, it's very helpful to have, but I just, the alternate signs are because you're plus, minus, you know, when you're doing your integrations, it's always UV minus this, so every time you do another one, it alternates sign. The U and its derivatives, x squared, 2x, 2, and then you get to 0, so nothing else will go there. Your V prime and its antiderivatives, and you list those out. And then you drop down 1, as they show here, those diagonal entries, which I don't know, I just don't find it that much more useful, but if so, go for it. I think after a while it would be. And there's another little blurb on the left about the tabular method. If you really want to look into that, there's a thing on the College Mathematics Journal, an article there, and then another one in the couple of them. So go to matharticles.com if you want to write a paper on those. But we finished 8.2. That's the big news. Homework exercises here. Any of the odds 5 through 9. They're all at Calc Chat. 5's at Calc View. Either 11 or 13. They're both at Calc Chat. 11's at Calc View. Any of the odds 15 through 33. They're all at Calc Chat. 15's at Calc View. 35 or 37. They're both at Calc Chat. 39's at Calc Chat. Slope field would be 41's at Calc Chat. And then any of the odds 43 through 51, all at Calc Chat. 45's at Calc View. 53 to odds 53 to 57, they're all at Calc Chat. 55's at Calc View. You can look into doing either 59 or 61. If you're interested, they should both be at Calc Chat. And here's Ricky. All right. And 61 or 65, they're both at Calc Chat. 67's at Calc Chat. 69's at Calc Chat. Any of the odds 71 to 75, they're all at Calc Chat. Any of the odds 77 to 81, they're at Calc Chat. 83 or 85 are at Calc Chat. And then any of the odds 87 through 91 are at Calc Chat. 93's at Calc Chat. 95's at Calc Chat. And either 97 or 99, they both should be at Calc Chat. Okay. Let's move on. Any questions? Okay. Now, I know that Kayla hasn't been here for a while. Why do I go over all those in the pieces like that and say them like that? Well, if you want to keep up with what's going here, even if you don't have the book, you can go to Calc Chat or Calc View and see the actual exercises that are in this book. They'll probably be very similar to the ones in your home book, but if you just want to see the others, they're there as well. And they're free websites. You don't need a code or anything. Just go to them. All right. Any questions? 8.2. So let's go. Oh, wait. Here was the table, so I didn't have to brush by it. Here we go. Here's how they do the table. Okay? Now, begin by thinking of u as your x squared, dv is your v prime dx, okay? Which is, in this case, your x squared is your u, and the sine 4x is your dx is your dv. So, they start by saying plus minus. You can do that for as many as you need here. The signs are always going to alternate. Well, you write down the u, x squared, then its derivative is 2x, and its derivative is 2. And here you get to 0, you know you're not going any further than this. Okay? The v prime, dv, that was your sine 4x, you just start doing the integration. And this keeps you from backing up and switching them. If you do the tabular form, you'll avoid that error. So sine 4x, antiderivative of this is 1/4, minus 1/4 cosine 4x. Antiderivative of that is minus 1/16. Sine 4x, antiderivative of that would be plus 1/64 cosine 4x, because that's same signs again. Okay. Now, that first v that you got here, that's the one that matches with this, so this is what goes your first term, minus 1/4 x squared cosine 4x. That's what we wrote down. Okay? Then you do the minus of the 2x times this one. See, this drops down 1. These are what we call the diagonals. But minus and a minus, that gives you a plus. 2 times 1/16 is 1/8 x sine 4x. There you got its answers without even having to do the individual steps. And then the next one is plus 2 times 1/64. That's 1/32. Cosine 4x, that's the last one. When you get to this, you see the 0 stop. You don't need to go any further. Okay? So, yeah, I'd say the tabular form, if you remember, that's the process. Start with the alternating sign. Always start with plus, plus minus, okay? And then write down your u part and just do all its derivatives, your dv part here, and then do all its integrations until you get to the 0. Once you got to that line, fill that one in because you dropped one, don't go any further. And you just do the antiderivatives as you go. Derivatives here as you go, and then that's your table. The sine, straight here, diagonal there. Straight here, diagonal there. Sine, straight, diagonal, sine. And there you have it. So it is a lot easier, especially if you have a whole passel of them to do. All right. Forgot they had that one there. So it's beneficial to see that. All right. The solution is obtained by adding the sign products of the diagonal entries. So that will be negative. Yeah, we've already gone through that. We worked it out in gory detail, and then they did it using just the diagonal entries. And that's the end of the slideshow for 8.2. Let's move to 8.3. It'll take a bit, but it'll come up. Here we go. We'll go from current slide. Still doing integration techniques and improper integrals, so we're not at the last part. Now we're going to do trigonometric integrals. There will later be trigonometric identities. Don't confuse the two. These are trigonometric integrals. Okay, 8.3. What these are, objectives here are to solve integrals involving powers of sines and cosines. Then we'll solve trigonometric integrals involving powers of secants and tangents. And then we'll solve trigonometric integrals involving sine-cosine products. So these are powers, sines and cosines, powers, secant and cosecant, secant and tangent, and then sine-cosine products. And if you remember back to your trig class, whenever you took it, however long ago that was, a lot of your trig identities that you did there, and you wondered, when am I ever going to use this? Remember they had sum to products, product to sum, some of those. Here is where you'll use those occasionally. Or look it up in a table. Okay? That's going to be what you end up doing most of the time. Sorry. So let's start. Integrals involving powers of sines and cosines. In this section, we'll study techniques for evaluating integrals of this form. Integral of sine m, sine to the mth x, the sine raised to the nth power x cosine raised to the nth power. Okay? The product of those, and secant raised to the nth power times tangent raised to the nth power, where either m or n is a positive integer. One of those has got to be a positive integer. The others could be other things, but one, either m or n, is a positive integer. Now, to find the antiderivatives for these forms, either one of these, try to break them into combinations of trigonometric integrals to which you can apply the power rule. Okay? So you're going to try to get it so that you can use a power rule with the trig function being the thing that you're raising to power. For instance, you can find the sine fifth x cosine x with the power rule just right now. A good old u substitution, let u equal sine x. Okay? du is going to be cosine x dx. Okay? And then you're going to have u to the fifth du. I can almost do that. Okay? Comes right out. That'll be u to the sixth over 6 plus c, and u is sine x, so it's sine to the sixth power plus 6, divided by over 6 plus 6. Okay? Now, if that were always just to the first power here, this would be a piece of cake, wouldn't it? That's just a u substitution, and that's all it is. But when you have a sine mx cosine nx, and neither of these is a 1, then you can break it into forms that you can apply the power rule, and here are the relationships. And you really should know this one without any qualification. Sine squared x plus cosine squared x equals 1. The basic Pythagorean identity. Okay? Now later when we do the secants and tangents, you'll use that version there. Now, here's the next one, and we did run into this in a previous problem. This very one. Sine squared is 1/2 of 1 minus cosine 2x. This is sometimes called the power reducing formula, sometimes called the half angle, or it's related to the half angle formula. Whereas cosine squared x is 1 plus cosine 2x divided by 2. Now, do y'all remember where those came from, or do you even care? Would it be helpful to you to remember that, to have an idea? Well, this one right here is always handy, so know that. Let me get my pen set up. But here's the other one to remember. I don't know if you remember the double angle formula. Double angle of sine, we're not going to use here, but I'll just write it down. Sine of 2x is equal to 2 times the sine x cosine x. We don't need it here. We will be using it a little bit later, but not here. But the cosine of 2x, there are 3 different forms you could write this, but to me the simplest or the most straightforward one is this one. Cosine squared x minus sine squared x. The other two get it all in terms of sine squared or all in terms of cosine squared, and there are advantages for those too. But with these two, this one and that one, okay? And here's what I mean. Let's just take this one and write 1 is equal to cosine squared x plus sine squared x. Yeah, I changed it a little bit, but not much. I just put this on this side, it reversed the 2, put the 1 over here. Well, what happens when you add these two equations to each other? Okay? Sine squares disappear, right? And you get 2 cosine squared x is equal to cosine 2x plus 1, or 1 plus cosine 2x. Okay? And then take half, and you got exactly this one right here. Sorry. Let me try that again. Okay? you get exactly this one right here. I wrote it in different order, but it's still there. 1 plus cosine 2x over 2, or cosine 2x plus 1 over 2. Same thing. Okay? And then the other one, if you subtract this one minus that one, okay, what would that give you? Now your cosine squareds go out, and you get 2 sine squared x is equal to 1 minus cosine 2x, and then divide by 2. There you get sine squared is equal to 1 minus cosine 2x over 2. So if you just remember this one, and of course you remember that one, combine them in these two ways and you get this. Okay? So if you can ever get your sine or cosine down to a square, then you can get to this form, integrate this. That's pretty easy to do. Okay? Okay. So you'll be using those a lot in this section. Not much anywhere else, but in this section you will. So here are the guidelines. Okay. When the power of the sine is odd and positive, power of the sine is odd and positive, save one sine factor out, convert the remaining sine factors to cosines, because if sine was odd, the power of sine is odd, pull out one, and then what's left is going to be even, and that even you can convert to cosines using your Pythagorean identity. Okay? And then you expand and integrate. So here's what it's saying. This is some odd number, 2k plus 1. That was our, what we were calling m before, is 2k plus 1, an odd number. We'll split that into sine of 2k times sine. Well, the sine of 2k, bring the 2 in with the sine squared x, and then raise that to the kth power, and you have, here's your remaining sine is out here with the dx. Okay? The cosine, doesn't matter what that is. It can be positive, negative, fraction, decimal, it doesn't matter what it is. Anything that n is fine. Okay? But this is going to be an odd positive integer. Okay? Your m. Okay? Pull out 1, making this an even positive integer. And then this is 1 minus cosine squared, and that's raised to the kth power. Cosine n, whatever that n is, it doesn't really matter. And then this is derivative of cosine. So you see, you get everything in terms of cosine, and that in terms of sine. Now, if k is a big number, you got a mess on your hands, but it's a doable mess because of Pascal's triangle. You know, remember that? That's fairly doable. Okay, that is, if sine is odd and positive, that's the procedure. If the power of cosine is odd and positive, do the same thing. Pull out a cosine and convert the remaining factors to sines and expand and integrate. So here, it doesn't matter what this m is. It can be positive, negative, fraction, decimal. It doesn't matter what it is too much. But this is an odd integer. Okay? So make it 2k plus 1. Okay? And same thing we did before. Cosine of 2k times cosine. There's the cosine. Cosine of 2k is here. We make that cosine squared here, raised to the kth power. And now this is derivative of sine. This is 1 minus sine squared to the kth power. And this is sine to whatever power that was. And now everything's in terms of sine and the derivative of sine. Well, plus or minus a SIGN sine. Okay. Now, when the powers of both the sine and the cosine are even, neither one of them are odd, so you can't use the easy way here. But both of them are even and non-negative. Okay. Then make repeated use of these formulas. Okay. Remember that was the second one. This was the first one, the Pythagorean identity, and this was the second one, the power reduction formula, the sort of getting toward the half angle formula, that kind of stuff. Then just keep using these over and over. If they're both even and non-negative, just keep going down with them, reducing the power each time. Of course, this will be going up. It'll be cosine of 2x and a 4x and a 6x and an 8x. It keeps going up, but then you just have cosines there, okay? Convert the integrand to odd powers of the cosine, whichever one you use, okay? Then proceed as in just everything's in terms of. Seems like if you have it in terms of cosine, you'd be here. First guideline, not the second one, but they say second. All right. You can see where to go from there. So here is an example. You tell me how to start. That was a lot of blah, 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 wasn't it? How do we start this one? I'll do the integral sign. I'll even do the dx, okay? Yes, you have one of the powers is odd. Sine happens to be that one. So pull out a sine x dx. What does that leave this sign to be? Sine squared x times cosine fourth x times sine x dx. Okay? Now, this is the derivative of cosine, plus or minus a sine. Okay? This is in cosine. Let's get that one into cosine. So what would that be? Integral of the sine squared into cosine. That's pretty easy. What is it? Please tell me it's easy. 1 minus cosine squared x times cosine fourth x times, let's just write it down, sine x dx. Okay? So expanding that, be the integral of 1 times cosine fourth is cosine fourth x sine x dx minus the integral of cosine 6x sine x dx. Okay? See what I did? I did, if you multiplied this through the cosine fourth x minus cosine 6x, all multiplied by that, so do this one minus that. Okay? Now, where would you go from there? If you can see how to do it straightforwardly, you can. If you need to do a substitution, do that. What do you want to do?
U is sine x.
U is equal to what?
Sine x. Cosine.
Cosine x. Good choice. Okay. Then du is equal to negative sine x dx. Okay? We want a sine x, so let's make that that. Right? All right. So what we have here is a failure to, no, it's the integral of u is cosine, so there'd be u to the fourth du with a minus sign out front, right? Okay. Minus, and it'll have another minus sign out front because it uses the same one, so that's going to be plus integral of u to the 6 du. And I think we can do those, can't we? What would that be? Okay. Plus u to the 7th. I don't know where the 6 came from. It started being a u, but it changed u to the 7th over 7. Plus c, of course. Okay. Then plugging back in, what u is cosine 7th x over 7 plus minus, sorry, cosine fifth over x over 5 plus c. All right, that's what I got. They put the minus cosine fifth in front. I don't know why, but then the plus cosine seventh. Okay. Now, looks like we got the same. Let's see if they did anything any different. Any questions about this before we move on? Okay. All right. Let me erase that. And let's see how they begin. Because you expect to use the power rule with u equal cosine, because that's the even, sine is odd. Derivative of cosine is minus sine, so that's where you'll put that odd one. Save one factor to form du, one sine factor. The lights I can hardly read with that, and convert the remaining sine factors to cosine. And how we do that is pull out the one odd sine one, put it over here with the dx, and then you have sine squared, cosine fourth, just like we did. Then the sine squared becomes 1 minus cosine squared times cosine fourth times sine x dx. So don't worry, that sine x is a d cosine with a sine or so in there, SIGN sign. So this will be cosine fourth minus cosine 6 times sine x dx, and then split those off. Integral of sine fourth x sine x dx minus integral of cosine 6x sine x dx, and then that will be, they don't like to use the u's sometime. I prefer them, but if you like them this way, it's fine. Since you know that derivative of cosine is minus sine, then this is minus sine x dx. Put a minus here, and then the minus from here makes that one a plus. To me, this is sort of backwards of everything else. But then, ultimately, I hope they use the u substitution. Nope, they just go straight for it and say this is your du with the appropriate sign there. That's your u to the fourth, so that would be. So without ever introducing the u, they go through this, and that's what minus cosine fifth over 5 plus cosine seventh over 7 plus c. I just like to leave off with the plus sign, so I reverse it, but it doesn't matter. Any questions on that? Same answer we got, just slightly different, and using a slightly different way. They say here a computer algebra system used to find the integral in example 1 yielded a different looking answer. And the question is that equivalent to the one we did? And I would say it better be, or else you better not use the computer algebra system. But if you went through and substituted for the sine squared that they had in their answer 1 minus cosine squared, and then did the math with that, I think you would come out the same thing. Okay? Now, in this first example, back here, both the n and m are positive integers. Okay? The only requirement is that one of them be positive and odd, or they both be positive and even. Okay? So let's do one in which, let's see if they do that. No, they don't. Okay, again, they're skipping so many examples. So let's do it here. Yeah. All right, example 2. Now, if you want to go to larsoncalculus.com, and again, for those who don't have this book, you can go there absolutely free and see this kind of example worked out interactively. Okay? And here we have a definite integral from pi 6 to pi thirds. That's not a very large range in your x. And in the numerator we have a cosine cubed x. And in the denominator we have the square root of sine x. And then we have a dx. Okay. First question. You want to leave it in this form? Please say no. No, we wouldn't think of it, would we? Okay. Why? Violates two of my cardinal rules. I don't like working integration or differentiation with radicals. And I don't like working with variables in my denominator. So it's got both of them. So let's rewrite it how? Yeah, cosine cubed x times sine to the what? Negative 1/2 x dx. Okay. Now, written this way, it looks more like what we were just looking at. What would be the requirement?
Take out a cosine.
One of them has to be an odd positive integer. The cosine is, take out one. You're absolutely right. So this would then be the integral from pi 6 to pi thirds of cosine squared x sine to the minus 1/2 x cosine x dx. Okay. Now what? Say next.
Cosine squared is the identity.
Okay, and what would that give us?
1 minus sine squared.
Perfect. Times sine to the minus 1/2 x cosine x dx. Okay. Now I'm going to distribute a little bit here. Be the integral from pi 6 to pi thirds. Okay, the first one's just going to be a sine to the minus 1/2 x cosine x dx, and the other one's going to be a minus integral from pi 6 to pi halves, pi thirds, I can't read, of what? Hint, I did the 1 times this to get that, and then just carried those with me. What's left?
Plus
I already filled out the minus. Say again?
plus sine x.
Okay, not quite. It's sine squared times sine to the 1/2. When you're, yeah, let me see if I can write one.
They get the sine over all papers today. Valuation.
Let me, maybe after, are you still here at 5:30? No.
Just about, I can wait.
Okay, you don't mind?
No.
Okay, let's do it then if you don't mind.
Yeah, yeah.
Okay, all right, thanks. Okay. When you're multiplying same base, different exponents, how do you do that? Keep the base, add the exponents. Don't multiply the exponents. That's why you don't like you did. When you add the exponents, what do you get?
Yeah, 3 halves.
3 halves. Okay. Maybe you said that. I don't hear well. So this is minus sine of 3 halves x cosine x dx. All right. Now what might we do with these? Yeah, I like it. Let u equal what? And this will be for both of them. Sine x, then du is equal to cosine x dx, and we happen to have one of those in both of them. So now our integrals will be the integral. I'm not going to put the limits yet. The first one would be, I'll write the u, the negative 1/2 du. Yeah, no, okay, yeah. And the next one would be the integral of the 3/2 du. Okay. Now what I've left off are my limits. Okay? So when x is pi 6, what is u? What are you? What's sine of pi 6?
1/2.
1/2. Perfect. Okay? So both of these will have a 1/2 down here. And when u is pi thirds, what is your, when x is pi thirds, what's your u? Square root of 3/2, is that what I heard? Yes. Square root of 3/2. Okay? Nice. Okay? So let's do that first integration. What do we get? Antiderivative of u to the minus 1/2 du. Okay, not 1/2, 1/1/2, which would be 2, right? You're raising a power and dividing by that power, which is dividing by 1/2 is the same as multiplying by 2, right? Okay? And let's just do them all together, and we'll evaluate them together. Minus, what's the next one? Okay, u to the 5/2 I heard, and what was the first? 2/5. Got it. And we'll evaluate this from 1/2 to root 3/2. Now this is where things get messy. It's not the calculus. The calculus is easy. It's fiddling with the other stuff. And this does get a little on the messy side. Okay? So let's start kind of forthwith here. This will be a 2 times the square root of the square root of 3/2. I hate writing it like that, but that's really what it is. Minus, I'm going to pull the 2 on the outside because both of them have 2's on them, okay? Minus 1/5, I'll put that down. The square root of the square root of 3/2 to the 5th power. Right? This is really ugly, okay? Minus, because we're using 1/2 now, and the 2's still out in front of all this, the square root of 1/2, and minus a minus, which is a plus 1/5, the square root of 1/32, I believe. Yeah. Because you're raising 1/2 to the 5th power, and that's 1/32. What a mess. All right. I'm going to leave the 2 out front for now. And this will be the square root of 6 over the square root of 2, I think, minus 1/5. The square root of 6 over the square root of 32 minus 1 over the square root of 32, 1 over the square root of 2 plus 1/5 times 1 over the square root of 32. Okay. Now, it would be 2, I say 2 and write 3. I don't know what's wrong with the brain. Okay. Have y'all just let me go over again? What were y'all thinking? Okay. I think it's far enough along that you can work it out. I sure hope it is anyway, because I don't want to. So go on and finish that one. You can go to larsoncalculus.com, see what happens. We'll start next time with example 3, but let's see if you got enough done for me to give a few homework exercises. I think you can do any of the odds, 3 through 13, stop there, and you've got the rest of it. So let me find my pencil. Here we go. We'll start with example 3 next time. And let me erase this. All right. Any questions? Then we'll see you on Wednesday, and hopefully I'll see you a little more clearly. But anyway, take care.